In this lecture, we're going to look at another example of a direct proof, this time about even numbers, and an example of how we can use a counterexample to prove that a statement isn't true. So here's our first the actual theorem we're going to prove. It says for every even number n squared is also even. So again, just what I talked about before, if it's not entirely clear to you what it is you're trying to show, it's helpful to take a statement like this and take it out of kind of this informal version and rewrite it in a standard if-then form. So the way I would write this, I would say if n is even, so that kind of tells me what I'm starting off with, then whoops, not 2 to the n squared is also even. So now I know where I want to end up, right? I need to show that n squared equals 2 times some integer. If I can do that, I'm home free. Okay, so let's start off our proof here, right? And I don't really need to per se do the universal instantiation part because I've already been given a variable. Right, I was told in the theorem that n is an even number. Okay, fine. There's no need to restate it. Right, I'm just going to go ahead and play off of what we already have up there. Right, I'm going to go directly to applying the definition. Okay, so I will say by definition, since n is even, there exists an integer k such that, and I'm going to do an equation here, so I'm going to go to the next line, right, such that n equals 2k. Good, there's kind of my setup. Right now, I know that what I want to talk about is n squared. Okay, well, fine. So what is n squared? So I would say, therefore, n squared equals 2k squared, which is 4k squared. Now, this is looking good, right? This is looking good, but at this point, I'm really trying to be explicit when I'm doing these proofs, right? So I really want to make n squared look like 2 times something, and I can do that just by rewriting the 4, right? This is equal to 2 times 2k squared, right? Then, right now we can wrap this up. Since 2k squared is an integer, by definition, n squared must be even. And that's what I wanted to show, right? So I'll put the QED down here at the bottom, and that's it. The proof is done. Right, so I'm still relying very much on this same kind of form as we've seen in previous proofs, right? I start by assigning a variable to what it is we're talking about, or using one that I was already given. Then I go to the definition of whatever it is I was told about in the premise, and I say, okay, well, what did the theorem tell me to talk about? Right? It told me to talk about the square of that number, so that's what I looked at. Right, and I worked my way through really still very algebraic sort of proofs to a final conclusion. All right, so how can we disprove something? Well, the standard way to disprove something is by finding a counterexample. Remember, we talked about this in a previous chapter. All it takes is one pair of numbers that don't make this true, that actually make it false. And that's enough to make the whole thing false. Right, so what I'm being told here is that the ratio of 2 even numbers is an even number. Well, okay, sometimes it is. Right, absolutely, sometimes it is. For example, if I let A equal 4 and B equals 2, both of those are even, right? And if I look at 4 divided by 2, that's 2. So sometimes it is, and that's nice, but that's not what this is saying if we're going to call this a theorem. If this is to be a theorem, then it has to apply for all pairs of numbers, and there are plenty of pairs of numbers for which it doesn't. For example, if I let A equals 6 and B equals 2, now the ratio 6 divided by 2 is 3, which is odd. And so this statement is in fact not true. And all it took was one example. There's lots of others, right? Lots of others you can come up with. But all it took was this one example to establish that it is in fact false. Okay, got some good proofs under our belt, right? We've seen, some good examples of how these direct proofs are done. We're going to continue this, look at some more examples in the next lecture. We're going to kind of take a break from odd and even and instead talk about rational numbers, right? Remember, rational numbers are the fractions. It's numbers that can be written as the ratio of two integers. And there is one quick point that I want to make before we go on and do that. I'm sure you noticed that I'm numbering the theorems here, right? This is the third chapter of our class, and that's where the 3 comes from, right? And the numbers that I put after them are just counters. The first theorem was 3.1, the second was 3.2, and so on. Their theorems are not officially numbered. Okay, if you go to a different textbook might have these same 2 theorems, and they might be presented later on, so they've numbered them differently, right? So, and that's fine, right? I'm doing this just for internal reference here in this class. Other authors use their own numbering systems, and it's internal to their textbooks, and that's fine. The only thing I want you to be clear about is please don't think you can go to somebody else and say, well, number theory theorem 3.2 says no. Okay, some theorems are sufficiently important, sufficiently special that they get their own names. Like the fundamental theorem of arithmetic that we're going to be talking about later in this chapter, but a lot of them aren't, right? So when that happens, you need to just state the theorem, right? It can be a little wordy sometimes. It can make your proofs a little wordy, but that is how it's done, right? With any theorem that wasn't special enough to rate its own name.